Hey guys, my name is IBM and I have decided to record electricity and DC circuits as requested by one of the students. Electricity and DC circuits, this could be about 4 to 5, uh, 4 to 5 lessons. I'll try my level best to give more examples. I'll try my level best to give more explanations on electricity and DC circuits. Don't forget we have covered most of the AS topics which include in AS you must cover physical quantities and units, errors and uncertainties, treatment of uncertainties. We have done already kinematics. We have covered dynamics. We have covered force, density, and pressure. I have covered work, energy, and power. I have covered deformation of solids, waves and superposition, electricity, and this particle physics. So currently, we are going to be dealing or focusing on electricity and DC circuits. And I think these, together with the waves, are the most important topics which carry a lot of marks, especially in paper 1. So, as you prepare for paper 1 and paper 2, make sure you spend more time on waves and superposition, and then electricity and DC circuits. So, waves and superposition, those are two topics, but I decided to make it one. Then electricity and DC circuits, those are also two topics. Electricity is current electricity, then DC circuits could be independent, but I chose to make it one topic. So we are going to focus on electricity. So like I said, this is AS physics and this is going to be lesson 1. This is going to be electricity lesson 1. Now if you're a teacher, the first part of electricity is simple and it relates to what students studied in IGCSE. Students who had a very good background in IGCSE do not need to be taught the first part of electricity in AS physics because the concepts are almost the same. All you can do as a teacher, you can just give more advanced examples. And then you concentrate on the second part, which is actually DC circuits rather than current electricity. But still, I'll record this. I'm recording this for my students because I'm very certain I won't teach this in class. I'll just send them to my YouTube and they watch this. Okay, so we are going to deal with electricity and DC circuits. And like I said, these are two topics. We have electricity and we have DC circuits. So, and electricity is where we shall cover concepts such as under DC circuits, we shall see practical circuits. We shall see Kirchhoff's laws, and of course, the Kirchhoff's laws are the most important concepts, or they are the most important under DC circuits or in AS physics. Then under electricity, we shall see, of course, circuit symbols, the same symbols you saw in IGCSE. We shall see electric current, the same electric current you talked about in IGCSE. We shall see potential difference in power, or PD and power, the same concepts studied in IGCSE. We shall see resistance and resistivity, the same concepts that you saw in IGCSE. Then, of course, under DC circuits, we shall not forget to deal with potential dividers. So, in AS level, if you're a teacher, you should concentrate most on practical circuits, potential dividers, and Kirchhoff's laws because a student is supposed to have enough information or enough ideas about electricity, that is electric current, potential difference, circuit symbols, resistance, and resistivity. Otherwise, let me start by reminding students about the first part of electricity. Before we explore the concepts of electricity, these are some of the learning objectives for this unit. You should be able to understand that an electric current is a flow of charge carriers. You should be able to understand that the charge on charge carriers can be quantized. We shall talk about the meaning of quantization. You should recall and use Q is equal to IT, that is an equation for charge equals to current times time. The same thing you mentioned in IGCSE. The only thing you didn't mention in IGCSE is using the current carrying conductor expression I equals to ANVQ. where n is the number density of charge carriers, or the number density, or the number of free charge carriers per unit volume, as we shall see later on. You should be able to define PD, or potential difference, across a component as the energy transformed per unit charge. You will be able to use V equals to W over Q, almost the same equation used in GCSE. You should recall and use power equals to IV, power equals to I squared R, and power equals to V squared over R. You should be able to define resistance. Of course, this resistance will be defined as PD per unit. Resistance will be defined as PD per unit current. And you should be able to use our V equals to IR, which is Ohm's law that we mentioned in GCSE. You should be able to sketch the IV characteristics of a metal conductor at constant temperature, a semiconductor diode, and a filament lamp. You may not have done this in GCSE. You should be able to explain that the resistance of a filament lamp increases as current increases because its temperature increases. We shall see that under the IV characteristic graphs. You should be able to state Ohm's law. You should recall R equals to rho L over A, that is resistance equals to resistivity times length over cross-sectional area. You should understand that the resistance of a light-dependent resistor decreases as the light intensity increases. We shall call this the negative coefficient. The negative coefficient LDR. We should also understand that resistance of the thermistor decreases as the temperature increases. It will be assumed that the thermistor has a negative temperature coefficient at this level. Of course, there are also thermistors with a positive temperature coefficient. Negative is just going to imply that as one quantity increases, which in this case could be temperature, the resistance decreases, giving a negative gradient. We shall see that in more details, most likely under potential dividers. Then we should also talk about the general recall and use circuit symbols given in the syllabus. We should be able to draw and interpret circuit diagrams containing the circuit symbols. We shall define and use EMF of a source as energy transformed per unit charge in driving charge around a complete circuit. We shall recall Kirchhoff's laws and understand that it is a Kirchhoff's first law and it is a consequence of conservation of charge. Kirchhoff's second law, we shall understand that it is a consequence of conservation of energy. We shall be able to derive using Kirchhoff's laws a formula for the combined resistance of two or more resistors in series. And we shall use the formula for combined resistance of two or more resistors in series. We shall derive using Kirchhoff's laws a formula for the combined resistance of two or more resistors in parallel. We shall use the formula for combined resistance of two or more resistors in parallel. And we shall use Kirchhoff's laws to solve simple circuit problems. Now, the content we are going to explore may not exactly follow the order of these learning objectives, but I have arranged them to my personal effect or to the way I want them to flow. So you should be able to understand the principle of potential divider circuits. You should be able to recall and use the principle of potentiometer as a means of comparing potential differences. You should be able to understand the use of the galvanometer in null methods. We shall understand what we mean by null methods. And finally, we shall explain the use of a thermistor, or you should be able to explain the use of thermistors and LDR and potential dividers to provide a potential difference that is independent on temperature and light intensity. So these are general learning objectives. Like I say, the content we are going to explore may not be exact in the order of these objectives because for instance, I can't start electricity before introducing the circuit symbols. Secondly, I cannot use Kirchhoff's laws before. Of course, I know that students have already explored effective resistance, combining of resistance in IGCSE. So I don't need to refer to Kirchhoff's laws when I'm talking about resistance or combined resistance. But of course, later we shall come back to Kirchhoff's laws in more details, and the student will realize that using Kirchhoff's laws, finding effective resistance is going to be very easy. Okay, I want us to start by reminding ourselves of the common circuit symbols that we shall find in this unit. So the common circuit symbols. You mentioned these circuit symbols in IGCSE, I suppose. So you saw the symbol for the cell. This should now become part of, if in case you forgot, the cell, the symbol for the battery. So of course, for the battery, remember the longer bar represents a positive, the shorter bar represents a negative. So for example, here it means we have three cells forming a battery. Or it can be represented like this. This is a battery. You have a collection of cells, they form a battery. That is a battery. Then a power supply. This is most like a DC power supply. When you see something like this, it's a DC power supply. One of these terminals will be positive, another will be negative. If it is an AC power supply, you may not always see AC power supplies in IGCSE, I mean in AS physics, but there will be a wave in between the terminals. One of them, of course, for an AC power supply, it keeps changing signs. In one half of a cycle, one side is positive, another side is negative. It's not like a DC power supply where um, the terminals remain permanently positive and permanently negative. Now, if I put an arrow into, for example, I put an arrow here, it becomes a variable DC power supply. In other words, a power supply which I can adjust from a certain value to another value. It becomes a variable DC power supply. Okay. Then we have a switch. You are used to a symbol for a switch. Then the earth. You are used to a symbol for the earth. The electric bell, a buzzer. You have seen these symbols in IGCSE, so I don't want to take much time about them. However, you should mark them and they should become part of you. You should be able to identify them in any electronic or electrical circuit. So we still have more common symbols that you'll find. We have a junction. Whenever two wires are meeting and they are actually joined so that there is a flow of current at that point is going to be made bold to mean that that is a junction. So current, sometimes wires may cross or maybe just crossing, but when they are not joining, but one is just on top of the other. But here it means they have broken them and then they linked them together so that current can branch at that point. So that is the symbol for a junction. When there is a junction, that part will always be made bold in a circuit. Then we have the symbol for a lamp. You are used to it in IGCSE. You are used to the symbol for a fixed resistor, variable resistor. The symbol for a thermistor, you are used to it in IGCSE. Then we have a microphone. You are used to the symbol for a microphone. You are used to the symbol for a loudspeaker. You may not really need the symbol for a motor, but that is how the motor is represented. You may also not really see this. You need the symbol for a generator at this level, but that's how we represent a generator. The symbol for the ammeter, you're used to it. So these two may not be very common, but knowing them does no harm to you. You still have more symbols. In IGCSE, you saw the symbol for a light-dependent resistor. You saw the symbol for a heater, I think. So you should be able to remember these symbols. You know the symbol for a potentiometer. You may not be knowing the symbol for a potentiometer, but it's almost the same as the symbol for the variable resistor, as we shall see under potential dividers. You should know the symbol for a diode, where this side is positive, the other side is negative. You should be able to remember the symbol for a diode. If the diode is emitting light, we add the arrows to show that it is a light emitting diode, which you call the LED, the light emitting diode. Then you should recall the symbol for a voltmeter. This one you're used to it. The symbol for a galvanometer. Then we have what we call an oscilloscope, even though you may not need this in GCSE, I mean in AS, you may need it in paper 4, yes, paper 5. You may need the symbol for the oscilloscope in a unit, in a paper called Planning, Analysis and Evaluation. You may not need a capacitor at AS level, but you will need it, or you will see this symbol in paper 4. That is in a unit called capacitance. So I think these are some of the common symbols, as the syllabus suggests. These are the common symbols you are supposed to know in this unit called electricity. These are the common symbols. Okay, you can test yourself or check your understanding and see if you can recall the names of all these symbols. You can pause the video and try to evaluate yourself. Okay, so I can also try evaluating myself. We have the ammeter, the buzzer, the cell, the power supply, which is a DC supply. We have the lamp, we have the electric bell, we have the LDR, light dependent resistor, we have the rheostat or the variable resistor, we have a switch, and we have a thermistor. So if you have recalled them like that, then it means you remember the names of these circuit symbols. Most of them you mentioned them in GCSE. Therefore, they should be easy to recall and they should be part of you. So we shall use most of them every time. The ones I've indicated here are the ones you'll commonly see most of the time, including the LED or the light dependent light emitting diode or just the diode. Okay, so those are some of the circuit symbols that we shall be using in this unit. Those will be some of the circuit symbols that we shall find in this unit. Okay, so let's talk about a simple circuit, simple electric circuits. So a circuit, I think a circuit is a path between two or more points along which an electric current can be carried. A path between two or more points, along which an electric current can be carried. So a circuit may have what we call a circuit breaker. You might have mentioned the circuit breaker in GCSE. This is a device which interrupts the path of current when necessary to protect other devices attached to the circuit. For example, in case of a power surge, a circuit breaker will prevent or will interrupt the path of current. So we draw a circuit using a set of symbols that are recognized by everyone and which do not need to be labeled. That's why I have been talking about these circuit symbols. So it is important that you learn these symbols such that you can always recognize them straight away. These symbols are used as shorthand method to draw complex circuits. The symbols are a small part of an international agreed conventional symbols for electrical components which all scientists, engineers, manufacturers, and others around the world use for a particular component. The International Electrotechnical Commission, we call it the IEC, is the body which establishes agreements on such things as electrical symbols, as well as for safety standards, working practices, and so on. So the IEC, we call the IEC 60617, I think. Thus, there is a less likelihood that misunderstandings will arise between people of different countries because the IEC determines the symbols for all the electrical components that we know in everyday life. So in simple circuits, therefore, we shall be using some of or all of these symbols in most cases because they are internationally agreed. And if I use a known symbol, I don't need to even label it because it is internationally known. But of course, like in paper 5, where we shall be using other diagrams to represent specific components which are not actual symbols. So in paper 5, we may need to always label the diagrams we have used to represent certain symbols. For example, you may not know the symbol for an oscilloscope. You draw anything and label it oscilloscope. But if I draw something I'm sure that is an international symbol, then I don't need to label it because it is expected that everyone must be aware of such a symbol internationally. So in simple circuits, we shall be using such symbols. So a simple circuit or a simple electric circuit consists of a power source, a conductive material like a wire, and a load. The load is where the power is going to be used or the power is going to be dissipated. So for example, a cell connected to a torch bulb by a wire makes a simple electric circuit. When the circuit is closed, the torch bulb is expected to light up. So that is what we call a simple circuit, a simple electrical circuit. And when it's open, the path which the electricity travels along is broken and the torch bulb goes off. So it's like a circuit is a path along which the current is supposed to flow, along which the electricity is expected to flow. So in many cases, you may need to add a resistor to control the amount of electricity traveling through the load. So you are now improving or modifying the circuit. And the resistor stems, it reduces the flow of electricity, allowing the target to function without becoming damaged. So in some circuits that we shall be seeing, we shall find their resistors incorporated so as to protect the components. Sometimes we may have, for example, a diode which does not need a lot of electricity. So to protect it, we may add a resistor in series maybe to protect the diode. So the question you may ask yourself, why should I use circuit symbols? Why use circuit symbols? Imagine that in practice, in the laboratory, you have connected a circuit like this one here, which um, incorporates a bulb. It incorporates a light-dependent resistor. This is how the LDR looks like in the real sense. It comprises of a bulb. This is a rheostat in the real sense, but a rheostat is a variable resistor, and it consists of a cell. So this is how exactly the circuit looks like. But you may not always be able to draw all this. Each of the components here has its scientific symbol or its electrical symbol. For example, we know the cell, we know the symbol for a cell as being, or a battery or whatever, as being something like this. We know the symbol for the rheostat as being something like this. We know the symbol for the bulb, and we know the symbol for the LD light dependent resistor as being something like this. Sometimes it is circled. So instead of drawing all these components, we would prefer to use circuit symbols. So circuit symbols are used as they allow complex circuits to be drawn in a clear and a precise manner, which is easily understood by anyone studying the image. So you notice that this would be even more precise than drawing this. Even though here I added a battery instead of a cell, but this would be more precise instead of drawing this because it incorporates a battery or a cell, whatever. Of course, many cells will form what we call a battery. Then we have a rheostat or a variable resistor. And you may notice that the bulb was connected across the LDR or the light dependent resistor. In other words, we would say that the bulb is in parallel. Many times whenever there is a junction, this part is going to be made bold, as we have seen earlier on. So this would be easier and precise as compared to drawing the full representation of the diagram. That's why using circuit symbols may be very, very important. So here is a simple activity for us to do. Draw a circuit diagram for a circuit with the following components. One cell. So you should be knowing the symbol for a cell. One light bulb. You should be knowing the symbol for a bulb. Connected in series, we shall of course understand, of course you know what we mean by series from GCSE. Two resistors connected in parallel. So you have two resistors that are connected in parallel. So in the laboratory, of course, your teacher should ask you to connect the circuit, or you can try to connect the circuit and see how it looks like in the laboratory. Okay. So in drawing the circuit diagram, identify the components and their symbols, and then you draw according to the instructions. So of course, if I combine a cell in series with a bulb and then two resistors in parallel, I would come up with something like this. There is no switch involved, so this is a resistor, and this is a bulb. I've used only symbols, and this is going to be the cell. So I have just used circuit symbols to come up with the circuit without necessarily drawing the components themselves. You can try to connect this in the laboratory, but this is IGCSE. You must have done this in IGCSE. Number 2, draw the circuit diagram for a circuit which has 3 cells. You should be knowing the symbol for a cell, but there are 3 in a series. So there are 3 cells in series. How do you join them in series? These are in series. You must have done this in IGCSE. One light bulb, you should be able to draw the symbol for a light bulb connected in parallel with the one resistor. So this should be in parallel with the resistor. And a switch. So there should be a switch. You should be knowing the symbol for a switch with the cells. So you can connect this in the laboratory, and I expect you to have come up with something similar to this. I think it looks like that. So you have 3 cells, 1, 2, 3. They are connected in series. In the series, we have the negative joined to the positive, the negative joined to the positive, and so on and so forth. So you have 3 cells in the series with a switch, and we have the bulb. The light bulb is connected in parallel with the resistor. So we see that these are in parallel. Like I said, in most cases, these points will be made bold to show that there is a junction here. So this is a simple circuit, and you should be able to connect such a circuit in the laboratory. You should be able to connect such a circuit in the laboratory. Okay. So more class activities. So for this part, for this class activity, you just need to pick the apparatus, try to follow the instructions, and then connect the diagram. You connect, you connect the circuit, and then look at the circuit, and then draw the diagram as you look at the circuit. Of course, you are not supposed to draw the components, how they look like. You're just going to draw a circuit diagram using circuit symbols to represent the components that you have connected. So this activity is just to help you to be able to interpret a connection or the connected circuit and relate it to the circuit symbols, and you should be able to draw in a precise way how it would appear or how it should appear on paper. So with the guide of the teacher, you should be able to do this. Of course, in my class, I just give them 10 minutes as I move around because there are always not very many students. So I give about 2 minutes for each activity. 2 cells, a switch in series, and light bulb, which is in parallel with the 2 identical resistors of 5 ohms. So just pick the components, connect, it should be working, and then you draw the circuit. Part B, two bulbs in parallel connected to a rheostat, which is in series with a 4.5 volts DC supply and a switch which turns on or off only one bulb. So the student should be able to make such a connection, and the switch should only turn off one bulb. It means the other bulb should continue lighting when the other one is turned off. The student should be able to connect that. Two lamps in series with an LDR, a switch, and a 4.5 volts DC supply. Include an ammeter to measure current in the LDR and a voltmeter to measure the PD across the LDR. Shine some light above the LDR and observe the ammeter and the voltmeter. Of course, I expect you to see changes in the ammeter reading and the voltmeter reading. If you use the torch of your phone to shine some light on the LDR, you should be making such observations if your circuit is correctly connected. And finally, you should be able to connect a lamp, a 12 ohm resistor, and a diode. All these three are in parallel, but they are then connected to an LDR, which is in series with a DC power supply of 4.5 volts and a switch. Include an ammeter to measure current through the diode. Of course, we shall later on see that the ammeter is joined in series, and a voltmeter to measure PD across the LDR. In IGCSE, you mentioned that the voltmeter is connected in parallel. So these are just to make you confident with using circuit symbols. Okay, so that is an introduction to the simple electric circuits. We shall come back to DC circuits under Kirchhoff's laws. Let us now start electricity or electric current. But of course, these are still the same concepts you studied in IGCSE. Electric current. So in IGCSE, you defined electric current as the rate of flow of charge carriers. In IGCSE, you defined electric current as the rate of flow of charge carriers. In other words, it is charge flowing through a circuit per unit time. That is how you defined electric current. The charge or the amount of charge flowing through a circuit per unit time. The rate of flow of charge carriers around a circuit. When I say rate of flow, I don't repeat myself by saying per unit time, because rate of flow means with respect to time. So when I say per unit time, I'll be repeating myself. Therefore, electric current can simply be charge divided by time taken, as you mentioned in IGCSE. Therefore, I is equal to Q over T. And the charge carriers could be electrons, they could be ions, positive or negative ions, but most commonly we shall be talking about electrons. And the charge Q is going to be measured in a unit called the coulombs. Of course, time is going to be measured in seconds, and the current is in amperes. Remember, the second and the amperes are SI base units. So it means the coulomb is being expressed in SI base units. When I make Q the subject in this expression, I is equal to Q over T. It means that Q is equal to I times T. In other words, if Q is equal to I times T, it means I can define the unit for charge, which is the coulomb, as the unit for current times the unit for time. In other words, the unit coulomb can be defined as ampere times second. So you'll be asked to define charge. So charge is simply product of current times time. There's no any other definition for charge other than a product of current times time. That is charge. And because current is a base quantity whose unit is the ampere, and time is also a base quantity whose unit is the second, then it means the unit for the unit for charge, which is the coulomb, will be defined as ampere times seconds, or ampere seconds. That is the unit for charge. So one coulomb is going to be defined as the charge passing any point in a circuit when a steady current of 1 ampere flows for 1 second. But precisely, we shall define a coulomb as ampere times seconds. So the column was named after a French, I think is a French physicist in the name of Charles Auguste Ducolomb. Charles, of course, I think in the French this would be read as Charles Auguste Ducolomb, the first scientist to study the electrostatic interaction between electrically charged particles. So the unit for coulomb is named after a person. That's why it is actually capital letter C. And then, of course, we know the ampere is the current flowing in a circuit when a charge of 1 coulomb passes any point through the circuit in 1 second. We shall fully define the ampere in a unit called magnetism, I think. That is in paper 4. We may not define the ampere in AS physics. However, the unit ampere helps us to define the unit for charge, which is the coulomb, because after all, ampere is a base unit, and therefore it can help us to define other units such as the coulomb, which are being derived. Many times we shall use the prefixes when talking about current. For example, milliampere, milli standing for 10 to the power of minus 3. We shall talk about microamperes many times, micro standing for 10 to the power of minus 6. So those will be the most common prefixes, I think, with the current as we progress. So because current is the rate of flow of charge carriers, and we have seen that current is charge divided by time. It means that if I sketch or plot a graph of charge against time, the gradient should give me the current. So the gradient of a graph of charge transferred against time should give me the current. So if I have a graph of charge against time, the gradient should be the current, because we have said the current is the rate of flow of charge carriers. And if on the vertical you have charge, on the horizontal you have time, it means that the gradient of this graph is going to be actually the current. Somebody may even think that the area under this graph would be the charge, but that will not be the charge for this case, because if this is a triangle, the area of this is going to be a half times Q times T. So it's like if the area is a half, let me just write this. The area under this graph is going to be a half times Q times T. We can't say that the area is the current, because the current is equal to charge over time. So the area cannot be the current. Q times T cannot be the current. But if it was a graph of I against T, if it is a graph of I against T, I think the area is the charge. Graph of I against T, if it is a straight line, if I am to find the area here, the area will be equal to half times I times T. It means twice of the charge would be equal to I times T, because I times T is charge. So it means the area will be twice. The area would be twice the charge. So there's a relationship between the area under the graph and the charge. We shall see that in A level, not at this level. All we need to know is that a graph of charge against time, its gradient is going to give us the current. And a few things we need to recall from electric current and charge, which you also mentioned in IGCSE, may include the following. Number one, all matter is made up of tiny particles, which you call atoms, each consisting of charged nucleus with the negatively charged electrons are moving around it. You must have mentioned this, or you'll mention this under particle physics. And there are two types of charges, the positive and negative. We know that from IGCSE. From IGCSE, you also remember like charges are supposed to repel. Like charges are supposed to repel and unlike charges are supposed to attract. And this accounts for the movement of charges around the circuit. Because like charges repel and unlike charges attract, then we can have free movement of charges around the circuit. The negative charge, I think you mentioned it to be about negative 1.6 times 10 to the power of minus 19 coulombs. And this magnitude of 1.6 times 10 to the power of minus 19 coulombs is what we shall call the elementary charge on an electron. You must have mentioned this in particle physics, and we shall always recall it E, elementary charge. And you might have mentioned somewhere that atoms normally have an equal number of positive and negative charges. Therefore, the overall charge on them is always considered to be zero. So when we talk about an atom, we are actually referring to a particle with zero charge in overall, because they always have an equal number of positive and negative charges. If an atom loses an electron, thus remaining with more positive charges than the negative charges, then it is normally said to be a positive ion. You mentioned that in chemistry. So we know what we mean by a positive ion and a negative ion. So if an atom loses an electron, thus remaining with more positive charges than negative charges, then it is a positive ion, and the reverse is true. If it gains an electron, it has more negative charges than positive charges, so it becomes a negative ion, and so on and so forth. But this is mostly a concept needed for chemistry. So let's try to do a few examples that I expect that you may not have done for your IGCSE, but they are still very easy, just to distinguish IGCSE concepts with maybe AS level physics. So convert 25 milliamperes to 25 milliamperes to amperes. Of course, you should know what milli stands for. Milli stands for 10 to the power of minus 3. So in removing a prefix, your teacher must have taught you this in the first unit of physical quantities and units. To remove a prefix, we multiply by its value. So this would be times 10 to the power of minus 3, which is going to be 2.5 times 10 to the power of minus 2 amperes. So part B, 0.5 amperes to milli. So in removing a prefix, I said we multiply by its value. In removing a prefix, we multiply by its value. In bringing back a prefix, we divide by its value. So we have 0.5 to milliamperes. That would be 0.5 divided by 1 exponent minus 3. So I think this would be 500 milliamperes. Mega to milliamperes. So first of all, we remove mega. In removing a prefix, you multiply by its value. Mega is 10 to the power of 6 amperes. Now, in bringing a prefix, we divide by its value. So this would be 25 times 10 to the power of 6. Again, divide by 10 to the power of minus 3, which gives us 25 times 10 to the power of I think that is 9 amperes or milliamperes. So 25 megaamperes to milliamperes will become 25 times 10 to the power of 9 milliamperes. So in removing a prefix, we multiply by its value. In bringing a prefix, we divide by its value. Question: to a torch bulb passes a current of 120 milliamperes. How many coulombs of charge flow through the lamp in 1 minute? So time is 1 minute. We want coulombs. So charge equals I times T. So this is 120 times 10 to the power of minus 3. Time is 1 minute, which is 60 seconds. So I just multiply 120 times 60 exponent minus 3. So this gives me 7.2 coulombs. How many coulombs of charge flow through the lamp in 1 hour? So charge is going to be 120 times 10 to the power of minus 3. 1 hour is 3,600. And I think that should be correct. How many electrons leave the negative terminal on the cell each second? Now, this is the only thing you never mention in IGCSE. So we want a number of electrons. Remember, charge is going to be equal to the number of electrons times the charge of each electron. That is the charge. But this is the same as current times time. So we want the number of electrons n. Like I said, this is the only thing you never mention in IGCSE. So the number of electrons is going to be I times T divided by the charge of each electron. So this gives you 120 times 10 to the power of minus 3, then times T, the time is 1 second, divided by the charge of each electron, which is 1.6 times 10 to the power of minus 19. So this is the number of electrons. I can check with my calculator. 120 exponent minus 3 divided by 1.6 exponent minus 19. So this answer is correct. Calculate the current that gives rise to the charge of 150 coulombs in a time of 30 seconds. So we want charge, which is I times T. So I just multiply 150, calculate the current. So the current is actually charge divided by T, which is 150 divided by 30. So I think here the answer is going to be 5 amperes. In a circuit, a charge of 50 coulombs passes a point in 20 seconds. Calculate the current. So we know current is going to be equal to charge divided by T. 50 divided by 20, which is, I think that is 2.5 amperes. A car battery is labeled 50 ampere hour. This is read as 50 ampere hour. This means that it can supply a current of 50 amperes for 1 hour. For how long could the battery supply a continuous current of 200 amperes needed to start the car? Of course, if in 1 hour it supplies 50 amperes, then it means 200 amperes can only be supplied for 200 divided by 50, which is 4 hours. So the time is going to be 4 hours. Then calculate the charge which flows past a point in the circuit in this time. So charge is equal to I times T, where the current is 50 amperes and the time is 4 hours. So that is going to be 4 times 3,600. So this is going to be 50 times 4 times 3,600. So this is 7.2 times 10 to the power of 5 coulombs. So that will be the charge that will be flowing in that case. Because charge is IT and the current is 50 amperes in a time of 4 hours. So that will be 7.2 times 5 times 10 to the power of 5 coulombs. The current in a circuit is 0.4. Capture the charge that passes a point in the circuit in a period of 15 seconds. So that is direct charge is equal to IT, which is going to be 0.4 times 15, which I think is going to be 0.4 times 15. This must be 6 coulombs. Okay. So these are IGCSE questions apart from where you're supposed to find the number of electrons, but they are very easy. A heater is labeled, a heater is made from a wire of resistance 18.0 ohms connected to a power supply of 240 volts. The heater is switched on for 2.6 megaseconds. Capture the power transferred. Of course, we are going to see this later on, but of course, from your IGCSE concepts, you should be able to solve this from power equals to maybe I squared R, power equals to I times V, and power is equal to V squared divided by R. So I'll use the last part of the equation where I have V and R. So this could be 240 squared divided by 18. I'll use the last part of the equation. So 240 divided by 240 squared divided by 18. I think that is 3,200 watts. Then the current in the heater, of course, we know that current, we have the time and we have the charge. So current can be Q divided by T. So Q is, sorry, I'm taking the resistance as the charge. So I can still use power is equal to I squared R to find the current. So, or I can even use V equals I times R, which implies that because I have R and V, then the current I is equal to V over R, which is going to be 240 divided by 18. Although we are going to talk about this later on, it is still IGCSE concepts. So this is about 13.3. Then calculate the charge passing through the heater in this time. So we have now the current. I think this is going to be, I think this is 40 out of 3 to be specific. So the charge is IT, where the current is 40 out of 3 times time. Time is 2.6 megaseconds, so times 10 to the power of 6. That is to remove mega. So 40 out of 3 times 2.6 exponent 6. So the charge is 3.5 times 10 to the power of 367, power 7 coulombs. Then the number of electrons per second passing a given point in the heater. So number of electrons is equal to the charge divided by E, because remember charge is the number of electrons divided by times E. So I can just divide this by 3.5 times 10 to the power of 7 by the charge of an electron, which is 1.6 times 10 to the power of minus 19. So this is going to be equal to 1.6 exponent minus 19. So this is approximately 2.2 times 10 to the power of 26 electrons per second. Okay, so that is going to be the number of electrons per second. No, this is the number of charges which pass in a time of 2.6 megaseconds. I think this is not the answer to this question, because the one number of electrons per second, that is the current flowing per unit time. So this is not true for this part of the question. So number of electrons per second passing a given point in the heater. Let me check. So the number of electrons is going to be equal to, of course, we know charge is equal to the number of electrons, which is the same as I times T, but the time is 1 second. So N is going to be current, which is passing a point per unit time is 40, or the current in the heater is 13.3. So this is going to be 13.3 or 40 over 3 times time, which is 1 second, divided by the charge of each charge carrier, which is E, that is 1.6 times 10 to the power of minus 19. Okay, so that is per second, because the current is the rate of flow of charge carriers per in time, which is the number of charge carriers passing in point in time per second. So if the current is the rate of flow of charge carriers, that is charge per unit time. So if in a unit time of 1 second, the current is 40/3, so it should be 40 divided by 3 divided by 1.6 exponent minus 19. So I think the correct answer to this would be 8.3 times 10 to the power of 19. What I got before is the number of charge carriers passing through the heat in a time of 2.6 megaseconds, not in 1 second. An electron beam in a beam tube carries 125 microamperes. What charge is delivered to the screen in the tube every second? So charge is going to be I times time. The time is 1 second. So the current is 125 times 10 to the power of minus 6 times 1 second. So the answer is going to be 1.25 times 10 to the power of minus 4 coulombs. How many electrons hit the screen each second? So remember charge is equal to the number of electrons times the charge of each electron. So it means the number of electrons is going to be the charge, which is 1.25 times 10 to the power of minus 4, divided by the charge of each electron, which is 1.6 times 10 to the power of minus 19. Then when I press the calculator, I think that is correct. A car battery is rated 36 ampere hour. In principle, this means it could pass a current of 36 amperes in 1 hour before it runs down. How much charge passes through the battery if it is completely down? So if it is completely down, we want the charge. How much charge? So charge is equal to I times T. So this is going to be the current, which is 36 amperes times T, which is 1 hour, 3,600 seconds. So I press my calculator. 36 times 3,600, which gives us 129,600 coulombs, which is approximately 130,000 coulombs, which is correct. Okay, so those are some of the examples, but all you need to note is you should be able to use a charge being equal to the number of charge carriers times E, which is the same as I times T. So you should be able to find the number of charge carriers. It is the only thing you never mentioned, I think, in GCSE. Let's talk about quantization of charge or of electric charge. This you never mentioned it in GCSE. What do we mean by quantization of charge? So when we talk about quantization of charge or charge is quantized, we think about Robert Millikan's experiment of around 1912, in which I talk about several other quantities being quantized. So Robert Millikan around 1912 performed some experiment to determine the charge on an electron using charged oil droplets, but his results show that no matter what the charge on the droplets, it seemed to occur only in integral multiples of E, the charge on an electron. Of course, we have already seen that E, which we call the elementary charge, was 1.6 times 10 to the power of minus 19 coulombs. We shall talk about Millikan's experiment in more details in A-level physics, but experiments show that every time, I think we shall see this in quantum physics maybe, or in electric fields. So every time Millikan tried to find a charge on an oil droplet, it seemed to occur only as a multiple of E, or only as a multiple of 1.6 times 10 to the power of negative 19 coulombs, which meant that 1.6 times 10 to the power of minus 19 coulombs was supposed to be the smallest charge possible, and all other charges were expected to be multiples of 1.6 times 10 to the power of minus 19 coulombs, which is called the elementary charge today. So the conclusion was that charge is not continuous. It is not continuous as we expected, but instead it is going to be said to be quantized. In other words, it only exists in restricted discrete amounts. Charge was not taking on random values. It was not taking on any value. It was not taking on continuous values, but it was taking on values which were multiples of a certain number which was already established to be 1.6 times 10 to the power of negative 19 coulombs. Because charge was only existing in restricted discrete amounts, we say that charge is quantized. So by quantization, we mean that charge of any particle must be an integral multiple of 1.6 times 10 to the power of minus 19 coulombs. So every time someone talks about charge being quantized, is referring to charge of any particle being an integral multiple of 1.6 times 10 to the power of minus 19 coulombs. It is an integer multiplied by 1.6 times 10 to the power of minus 19 coulombs. Remember, we have already mentioned that E is the elementary charge, which is 1.6 times 10 to the power of minus 19 coulombs, and it will sometimes be called the fundamental charge. We expect that 1.6 times 10 to the power of minus 19 coulombs is the smallest charge possible. That's why we shall call the elementary charge. So when we talk about charge being quantized, we refer to the fact that charge does not take on any random values, but it takes on specific or discrete values which are multiples or integral multiples of the elementary charge. It should be an integer or a whole number, both positive or negative. So the charge of any particle is n times E, where E is the elementary charge, and n is a whole number, whether positive or negative, which we prefer to call an integer. So charge can be positive or it can be negative, but should be a whole number multiplied by 1.6 times 10 to the power of minus 19 coulombs. Other quantities we shall talk about as being quantized could include the photon, or the energy of electromagnetic radiation, which is a photon. So the photon is another example of quantized physical quantity, which we shall discuss in a topic called quantum physics. This will be in paper 4, that is A-level physics. So charge is quantized. So to understand the meaning of quantized, let's consider 2 points where an object, for example, has to be put. We have to bring an object to this level, but we have 2 options, either to take the steps until that level, or to just pull the object along an inclined plane. So in taking the steps to reach that point, the object must always be on a specific step. But in pulling it along the inclined plane, the object will now have continuous increase in gravitational potential energy. So here we say it is quantized, here we say it is continuous, here we say it is discrete, here we say the energy will be continuous. So when we say charge is quantized, we are referring to this part here. Charge will only have specific values, not any random values. And these values are whole numbers or integers multiplied by the elementary charge of 1.6 times 10 to the power of minus 19 coulombs. So that is what we mean by charge being quantized. So you may be asking yourself, how does really conduction of electricity take place? You might have also talked about this in your GCSE concepts of conduction. What really happens during conduction of electricity, and why is it that current flows almost instantly? Of course, we know that in metals we have free electrons, and these free electrons are always in continuous random motion. However, they may not really be aligned in any particular direction for current to flow if the circuit is not complete. But when a battery is connected across a metal wire or a conductor, There is an electric field which is set up within the conductor, which travels through the conductor at almost the speed of light, approximately 3 times 10 to the power of 8 meters per second. So this now makes the electrons, which were already available in the conductor, but which were always in continuous random motion, to now be aligned up, or to be lined up in one particular direction and to be accelerated by an electric field. So these electrons are going to be aligned up and are going to be accelerated by an electric field, and this flow of electrons is what we call, or what constitutes, current electricity. So a charge carriers already exist in the conductor if it is a good conductor. All we need is to line them up in one particular direction and then accelerate them. And if they are accelerated and lined up in one direction, then a current flows within the conductor. Of course, we know that the current flows in the opposite direction to that of the charge carriers of the electrons, according to Benjamin Franklin. So, as the electrons move, they collide, of course, with the atoms in the lattice, and they give up or lose some of their energy to the atoms. The atoms begin vibrating with increased amplitude, and heat is generated as the atoms rub against each other, causing the heating effect in the wire. Sometimes if you were charging a phone and you pull out the charger, you notice that the charger has warmed up. So what essentially has been happening, as the electrons move through the conductor, they collide with the atoms, transferring some energy to these atoms, causing these atoms to vibrate even more. It's the vibrations of these atoms which result into heat, or which cause the heating effect of the wire. That's why the wire gets hot when a current is flowing through the wire. And this effect is what we call the Joule heating. So the heating action of electric current is what you call the Joule heating. This effect occurs even if the current in the wire is reversed. Of course, normally what the current flowing in our wires is always alternating current at home. And this current also can cause the wire to warm up, as we shall see in a unit called alternating current, that is in paper 4. So you should be able to explain why a wire carrying current gets hot. And I've given you a simple explanation to this. The electrons, or flow of current in a wire, is due to free movement of the electrons. The free moving electrons collide with the atoms and pass on some of their energy to the atoms. The energy of the atoms causes the atoms to vibrate, generating heat. That's why the wire will therefore, or definitely, will get hot or will warm up when it is carrying a current. So how does current flow then? So according to Benjamin Franklin, conventional current flows from positive to negative. You mentioned that in GCSE. According to Benjamin Franklin, conventional current, a convention is like a rule, a decree, an agreement. So conventional current flows from positive to negative. So the tall bar, the longer bar is positive, the short bar is negative. So according to Benjamin Franklin, conventional current flows from positive to negative. However, the charge carriers flow from negative to positive. So the electrons flow from negative to positive as the current flows from positive to negative. That's why we always put an arrow from positive pointing towards the negative to show that the current flows from positive to negative. Essentially, we would prefer to say that current flows from high potential to low potential, because we assume that the negative is actually low potential. So in this circuit, the direction of the current is from the positive terminal of the cell around the circuit to the negative terminal. And this is a scientific convention first suggested by Benjamin Franklin. Hence, we just agree by decree that current flows from positive to negative, but because the charge carriers are the electrons, and yet the negative terminal is negatively charged, we do not really expect electrons to flow from positive to negative again, because they would be repelled. So we believe that because electrons are negatively charged, they would therefore be flowing from the negative terminal to the positive terminal, as the current flows from the positive terminal to the negative terminal. Of course, this idea is still confusing, and it must be confusing to you, to any of you. However, if you try to think about it, you'll now understand that Benjamin Franklin's convention makes sense for current flow to flow from positive to negative, and the charge carriers or the electrons to flow from negative to positive. So we just call it convention. It is just a rule. The electron flow is from negative to positive, as the current flow is from positive to negative. So this is a convention. Electrons flow from negative or from the negative terminal to the positive terminal. In other words, negative charges repelled by the negative charge on the negative terminal. They would build up in the battery's negative terminal. Then by convention, the current of conventional current should flow from positive to negative. In other words, negative charges moving in one direction is equivalent to modeling an equal number of positive charges in the other direction. So it makes sense for us to think about current as flowing from positive to negative, because we believe that electrons cannot accumulate, cannot move to the negative, because the negative terminal would repel them. So we believe them to be moving from negative to positive. So if electrons move from negative to positive, it is equivalent to modeling an equal number of positive charges moving from the positive terminal to negative terminal. That's why we assume that conventional current should flow from positive to negative. So a few things we need to note from the flow of current. Number one, an electric device or an electric wire is made of metal. In the metal, there are negatively charged electrons which are free to move about. These ones we shall call them conduction electrons or free electrons. So for every wire, there are free conductors free conducting electrons. So a cell connected across, if we connect a cell across the ends of the metal, it just causes the electrons to drift towards its positive terminal, or the electrons to drift towards the positive terminals. And this is in the opposite direction to conventional current. So we have already agreed that current flows in the opposite direction to the current. And by the way, from your concepts of chemistry, you might have mentioned that a current can also be produced due to positive and negative charges. For example, when charged particles flow through a solution that you may have called an electrolyte. You might have talked about an electrolyte in chemistry, even though it's not very important for physics. But a solution which conducts is called an electrolyte, and it contains both positive and negative ions. So a current can also be produced from just positive and negative charges in a solution such as an electrolyte. These are expected to move in opposite directions when connected to what we call um, when connected to a cell. They should when the solution is connected to a cell through what we call electrodes in chemistry. You might have seen this in chemistry. You might have generated or you might have seen a current, or you might have noticed or detected a current using electrodes placed in an electrolyte, because in an electrolyte we have both positive and negative ions, and these are expected to move in opposite directions when connected in series with a battery or a cell, with the positive ions expected to move towards the negative electrode and the negative ions expected to move towards the positive electrode. But like I say, these are concepts. This is a concept for chemistry, not for physics. So I want you to also note that current tends to flow through the least resistive path. Current tends to flow through the least resistive path. That means if we cause a short circuit, if we short circuit, the current does not flow to the load with high resistance, but instead it takes the least resistive path. I always ask my students, would you prefer to be a billionaire without going to school? And their answer is always like yes, because everyone prefers to take the least resistive path. So current takes the least resistive path. So if we short circuit or we create a short circuit, or if we introduce a wire if we introduce a wire where current is able to dodge the load or the component of high resistance, the current will flow through a device. I mean, it will flow through a wire which has extremely less resistance and it dodges, going to one which has very high resistance. That's what we call short circuiting. So if we consider a circuit such as this one here, and we explain that when we close the switch, we cause current to flow through the bulb, and we explain that the bulb lights. But before closing the switch, we have what we call an open circuit. An open circuit is one in which there is no current flowing because the circuit is incomplete. So when we close the switch, we have what we call a closed circuit. So this is called a closed circuit because current is flowing and it has no any other option apart from going through the bulb. However, we can cause a branch somewhere before reaching the bulb where the wire connecting or the wire creating the branch has extremely low resistance. In that case, the current will not go through the bulb because this has a lower resistance and the current tends to flow through the least resistive path. So in that case, therefore, we have caused a short circuit. So this is what we call a short circuit. Whenever you have a path or whenever you have a less resistive path or the least resistive path in a circuit, current will not go through the component and it will just take the least resistive path. And in that case, we have what we call a short circuit. A short circuit is going to be very dangerous because it could even cause instances such as these ones here in the house. Whenever there's a short circuit, you may cause a fire. When you connect wires in such a way that current does not flow through the load, or it misses or it dodges going to the load, it just flows around the least resistive path back to the power supply, and this may cause it may cause fire in that case. So a short circuit is extremely dangerous because it may cause fire. So in any circuit you notice, if there is a short circuit, you are sure that current will flow through the least resistive path and it will dodge our load. So the bulb will not light in this case because there is a short circuit. We may just see fire instead of lighting the load because current is following the least resistive path. So you need to note that very carefully that current tends to flow through the least resistive path. And I think this should be the end of lesson one. I'm sorry for the interruptions about the noise. I think there was some construction, but I couldn't stop this because I'd already started it. Until next time, see you in lesson two. Bye bye.